Okay, so good morning, everyone. So many thanks for being today with us here for this MIS seminar. So Maria and I are today the chairs of the seminar, and we have the pleasure to have Sandra Chapman with us, which actually I think all of you know her pretty well, but I was having a look to the CV online, and I have to say, like, I'm really impressed, and it's really an honor to have you in here. Like, you have like an amazing career. And with not only a lot of hours, but with a lot of expertise behind, which is actually really amazing. And if you have an opportunity to have a read, I will recommend, because it's really truly inspiring. Like, since you got long ago some awards from GOSPAR, from the European Geoscience Union, but also recently from the American Geoscience Union. So this is really absolutely great. And it's an honor to have you with us today talking about space weather. And in particular, the title is Data Analysis Approaches to Space Weather in Space and Time. And just before starting the seminar, so I would like to everyone to remind that if you can mute yourself, just this is to avoid any extra noise that we may have. And also, if you have any questions, please write that in the chat, but please with copy to everyone. So because Sandra is sharing the screen, so she won't be able to see that. And we will have some questions and Q&A at the end of the talk. And also, if you want, there is the option to have some subtitles, and they are already activated. So you just need to click on the live translate at the bottom of your screen. So yeah, this is all from my side. So Sandra, when you want, you can start.
Okay, thank you very much. Okay, so what I'm going to do, I've got quite a lot of stuff. And of course, I said, well, it's about space weather, but really it's about methods as well. And so I'm hoping, even if you're not particularly interested in the detailed subject matter or the particular data, that you'll get something useful from the methods. They're quite generic methods. So really, hopefully it will give people something useful. And I'm going to do a lot of overview. So not go deep in the details. So I ask me questions afterwards. If you've got a specific thing, I can email, share things. So that's the approach, okay? So I'm basically going to talk about a few things. The first is, what do you do if you've got a whole bunch of observations and they're not uniformly in space? Okay, so this is like supermag magnetometers or something, but a lot of our observations are like this, okay, that are on the Earth. So non-uniform, trying to look at something that's temporary varying, okay, spatial temporal correlation. And then I'm going to look at what happens with the opposite, where you've just got like one observation, but you've got a long time series and you've got multiple time scales in there that you're interested in. Okay, and I'll finally have a recent idea about that is solar cycle clocks, okay, which is, again, it's about visualization as well, I think, which is called a side of what we do. Okay, so that's kind of what I'm going to try and cover. Now for some reason, there we go. Okay, these are the papers, right? I mean, I don't expect you to read it, but I'm covering quite a lot of stuff. So that's what I'm saying. I'm going to give the idea, and for technical details, ask me and I'll point you at the right thing or answer the question. Okay, so just for people who aren't, clued up on space, whether it's not their thing, just a brief introduction of what we're interested in. So we're interested in everything from the kind of prompt effects you get from a flare, to what happens when a CME reaches the Earth and causes a storm, to sort of lower level activity, substorm activity within storms or otherwise, okay? And this can affect everything, as you'd expect, from the performance of satellites, satellite communication, ground to aircraft, aircraft to aircraft communication, and of course magnetic field perturbations on the ground. If you've got a long piece of wire, be it a railway line or a power grid, all these kinds of things, okay? And so this is why we're in the sort of things we're interested in. And as you probably know, space weather is now on the National Risk Register. This pandemic flu, this risk register was created before COVID, okay? So then it was pandemic flu. So this is severity versus likelihood. So space weather's right up there, not in terms of, how often it might happen, but also the problems it would cause. Okay, so I'm going to start with the first thing, and that is, what if you've got like this? Hopefully this movie is working for everybody. This is one of Jesper's Supermag movies of a substorm, okay? And we've got lots of points, and we're measuring that the green lines are, they're actually the component of the magnetic field in the ground turned by 90. And you can see there's a substorm. You see a nice aurora happening. You know, the auroral images are superimposed. And, you know, you can almost imagine waving a bar magnet over the things, a giant bar magnet, because you can see the kind of field with a nice curl going on. Okay, so that's all lovely. But of course, we want something quantitative. We want to kind of put a number on that. And in the past, people have looked at indices. And I'll talk about indices later on. But, you know, the idea was maybe you pick the biggest guy, you know, AE, pick the one with the biggest excursion. But really, we want something that captures the whole spatial pattern. And so this is where the idea of networks comes in, okay? So this is a well-developed science in other fields, particularly sort of social science type stuff, you know, where you've got societal data, okay? But the idea is you can make just a few parameters characterize the spatial pattern, and they're time-varying parameters. Okay, so the event that I just showed you, here's our very first attempt at doing this. So what you do, just roughly, is you say, okay, I want to decide if a pair of stations are correlated. So what we're doing is calculating canonical cross-correlation because they're vectors. So canonical cross-correlation pairwise between all the magnetometer stations. So that will give you, you know, an array, okay? A sort of, you know, nice square array of values of each one and their correlation with the other. And this is cross-correlation. So you get this for each lag, because cross-correlation is a function of lag. So you've got lag as well. So there's are they immediately, instantaneously correlated, or are they correlated with a lag? And that's a kind of information propagation piece of information. So you've got direction as well buried in this. There's a lot of information. But the key thing is you have to decide how big the correlation has to be to count them as connected. And this is the extension from a kind of societal stuff, because if you're, you know, if you're talking about friends on a social network, either you're friends or you're not, it's kind of yes, no, but we have to do an extra piece of work. And that's a lot of technical detail of thinking about how to do this. We actually use the threshold, we calculate what the threshold needs to be to give the same likelihood of connection in the network. So the threshold is varying with season, it's varying, you know, across the magnetometers, where they are they in the sun or the shade, all this kind of stuff. So you have to do something like that, and that's detail I could discuss if people are interested. Okay, but having done that, then we can do something like this. And this is just the zero lag. Remember, there's a function of lag. And we've literally just taken the time at onset and colored in the connections. The green is within the oval and the red is across and the blue is outside. So you can immediately see the sort of, there's a current system there, which is kind of what we knew. So you can start to pick it up with the network. But we could do a lot better than that. You can say, well, actually, now we've got a network. Once you've created a network, remember it's changing with time and it's a function of lag as well. You can say, I can look for how patchy it is. Is it uniform? Is every part of the network connected to every other with the same probability? Or do you have little communities? And there's an idea in network science called community structure. And I'm just kind of showing it here. So the idea is, if you think about, you know, I want to go visit my friend. Okay, if my friend lives in the same town, there are probably many ways I can go to my friend. There are many paths. If my friend is in the next city, there's probably one way, you know, I go along the motorway or whatever, one or two ways. Okay, and so this is how you can define communities, by counting the number of ways and removing all the connections. And so you can get a parameter which, you know, which is kind of quantifies that. So this parameter is Q. So I'm going to remember, there's a lot of data, you know, there's a lot of information. So I'm trying to capture it for one substorm here in this little plot. So we've normalized time, okay? This is Jesper's way of kind of putting a substorm onto a uniform tide base, okay? And at the bottom, we've got SML and things, so you know where the substorm is. These blobs are trying to tell you where all the stations are and how connected they are. So you can see lots of little spots. The more connections they have, the bigger the circles. The colors are trying to capture the lag, you know, what's the lag of peak cross correlation. So if it's gray, that means they're correlated instantaneously, and the colors means that they're correlated with a lag. Okay, so all this information just for one storm, it's a substorm, you know, it's a lot. But the way to kind of, you know, condense it down is this parameter Q, which tells you about the community structure. And Q is high when you have lots of little communities, and it's low when you've got one big guy. And that's what you can see in the substorm, that it's high and then goes low. Okay. The gray guy is the surrogate. So everything we do, we want to know what it would do randomly. So you just take all the data, you Fourier transform it, shuffle the phases, transform it back. So it's got the same power spectrum, but now it's random phase, and calculate everything. What answer would I get? And that's the gray guy. So you can see this destroys all the correlation. So that's a kind of check. So that's just one guy. The interesting thing, and I think this is to get at the point of, you know, we want to kind of nail some stuff down here. So you can see what happens before onset. There's lots of little things going on. Okay, and then you see the substorm current wedge. You know, you see a big current system kicking off at substorm onset. And this is kind of what we found when we started to look at lots of events. Well, what happens before, just as the thing's getting going? You see lots of little patches. This is time increasing like this, okay, for one event again. And these are the little patches, the communities. And they get more and more connected. Eventually, they all form a big current system. Okay, so there's a transition from lots of little things to one big thing. There's always a transition when we've looked at many events, but you know, every time if you look just before, the pattern is different, which is kind of interesting when you think about how people are looking at the data and trying to decide what's going on. So another way, now we can look at 41 events because we've got a number now, okay, this network modularity that tells you, you know, how clumpy it is. And so that's what's going on here. This is time. So we've taken our 41 events, we've normalized the substorm length onto a, you know, uniform time base using Jesper's algorithm. You can see that the average modularity is high and then low. In other words, it starts off with lots of little things, ends up with one big current system. But if you look at the distribution, it starts off, all the different events, you know, have different amounts of clumpiness. Some have really got lots of little guys and some haven't. So it's all over the place. But once you get into the substorm, then you see, you know, one big value of Q here. In other words, they're all going to one big current system. So this is kind of telling you something about substorms, which might help us, you know, simplify the models a bit. Because if we look at the models, and the first thing to notice, these models are drawings, they're static drawings. And this is the thing I keep coming back to. I think it's an open question. We're trying to describe something that is not static. And so there's an ambiguity there, okay? But nevertheless, we'll go with this stuff and look at it. Different ideas of what's going on in a substorm. And we can now say, well, you know, we see the big current wedges is the McFerrin type idea that there's a disruption in the tail and so you form a big current system, okay, electrojet. It could be one big guy or it could be two correlated guys because, you know, those look equivalent under correlation between pairs of magnetometers. But what it can't be is lots of independent things because they're correlated. They're not just aggregated, you know, oh, lots of little things, we can't resolve it. They look like a big thing. They're actually cross-correlating and giving a value. So we know it's not that, or it's not that, you know, throughout the storm, the substorm anyway. It might be that early on. So this kind of, it means we can kind of sort this stuff out, but it also maybe gives us an understanding of the difficulty because if as you come into the substorm, every time it looks a bit different and people are looking at partial information, they might be looking at particular magnetometer chains or images or whatever. You know, every time they look, they're going to see something slightly different as you go into the substorm. And so there's going to be a lot of confusion and a lot of controversy. So this kind of study can maybe help us understand what's going on, sort out the controversy a bit, but also why there's a controversy in the first place. You can actually start including all the information. So that's the first kind of thing I wanted to talk about. So as I say, there's a lot of detail, but just to give the flavor. We can do something practical with it. So this is a collaboration with Karen Big and BGS. This is Lauren Orr's work. You could say, okay, well, why not ask this question of the national grid? So there's a, you know, there is a model for the national grid, and you can drive it. You can say, okay, let's consider it's a storm now, okay, and we've got a few magnetometer measurements, and so we can model an electrojet based on those and impose it on the model for the grid, and we could look at the cross correlation. Okay, I want you to notice. You see, there are these big long lines, the high voltage lines going across the country. Okay, because when you do that, and this is doing that, these are a few snapshots looking at a modeled storm, a big one, the Halloween storm. You can see it picks out, these guys, it's picking out these horizontal lines in the grid structure. So what you're doing is we're answering the question, well, you know, if we, and this was Karen's question, if you've got, you know, a signal in one part of the grid, can it tell you what's going to go on in the other part of the grid? You know, then that's quite useful. And the answer is, well, yes, it can, but it's not, it's very intermittent though. So you can see these kind of connections. It's, as I say, I won't show you a movie because we haven't got too much time, but the fact that, you know, I'm showing these at different times, these things come and go, they're very intermittent. So don't get the idea that it's highly connected for like hours. It's very intermittent, but they do convey information. So one part of the grid is dependent on another. Okay, and there are a few supernodes. So this is the other interesting thing. You find a few nodes where that guy's connected to everybody, and then other nodes that are not. So this is quite useful information. Okay, so there's a lot one could do with this idea, okay, in terms of trying to parameterize a lot of information which is not homogeneous. That, you know, like this nice model grid is not homogeneous. The magnetometers were not homogeneous. Okay, so I want to move on now. What if you just got one observation, but we're looking across time, okay, and across things happening on multiple timescales? So this is the question about, so the rest of the talk's going to be about solar cycle variation, but about trying to say something about likelihood of space weather events with imperfect data, okay? Okay, so the first problem is that a geomagnetic storm, we're going to talk about storms now, is much smaller than the background field. And so what drives indices and how we talk about indices is to try and, you know, get rid of the background field, which of course is not constant, because it's you know, it's telling you about the sort of quiet magnetosphere, and that changes with the season, and you know, there are, you know, where you're looking and all this kind of stuff. Okay, so some sort of active kind of correction or normalization has to happen, and you know, there are different things that are done. So one way of doing this is to construct indices, and of course we're going to talk about something like AE SME, which is basically picking, you know, the largest positive and negative excursion in the Aurora region and finding the difference between them, and SME is an improvement on that. And the other one is DST, which is essentially comes from an average. You're trying to talk about the ring current. So it would be an average of 4 stations that are corrected for their position, and SMR is a minute resolution version of this, okay? So we have these indices to try and solve this problem, and we have them for the space age. So we've got about 5 cycles. There are other interesting things where you might get an extra cycle, but not many cycles. Okay, and so I want to plot the data in a statistical kind of a way. So just a quick reminder for people, I'm sure people know what a PDF is. A CDF is just the integral of that. Okay, so it's the likelihood, you know, if I'm at, say, halfway across the data, you know, so Q is 0.5, and then this is X 0.5. If I order the data from small to large, I've seen the half of the data which is smaller than that value. The survival function is just 1 minus that. It's just easy to look at, okay? The point about these guys is that you can just get them from plotting the data without binning it, as I'll show. Okay. And this is kind of what I'm doing. So I'm plotting 1 minus C here, okay, for some quantities. So what I'm doing, I'm taking quantities over the last 1, 2, 3, 4, 5 cycles. I've colored them in. I'm literally taking the data and plotting. So this top guy, this is minus DST to make it positive. And this is AE. And you can see the different distributions. So like the last quiet cycle, you can see the purple guy, much smaller values. Okay. And the first interesting thing is to ask the question, well, you know, the question we're asking is this distribution is going to be different for every cycle? You know, this is a sample a year around maximum, or it could take 2 years or whatever. You take your sample and you say, well, is the whole distribution just floating up and down, or is it changing? And that's quite useful to know if you want to know what the next one's going to do. And the first thing we find is, okay, we expect these things to be multi-component because you're seeing the effect of large events, but you're also seeing the kind of fluctuations as well. So we know it's at least 2 components. So we're not expecting the whole distribution to do the same thing. But if you look at kind of the higher values, and I've marked what I mean by higher values. So this is the quantile, the 0.95 quantile, top 5% of data, okay? The 0.75 quantile, the top 3/4 of values. If I take those values and I just rescale to their mean and standard deviation, you see the thing kind of lines up. So that's interesting. It's kind of saying the thing's just floating up and down with the cycle. Okay. And then, of course, if you do that, you could then say, well, we can model it. And this is an attempt to fit a distribution, a generalized, a GPD distribution. Okay. And so now we've got a function. If we knew roughly how active any cycle is going to be, just the mean and standard deviation of values, we know what the full distribution is going to do. So so it's useful, but it's also kind of interesting as to why it's so. And I'll do a bit more about that. Okay, but just where did I get this line from? This one, you might notice, well, this one was 0.75, that's AE, and this one was 0.95. Why? I use the data to tell me where I am in the distribution. So if you've got a CDF now and you've got two samples, I've got one solar cycle, then another solar cycle, so things changed. And I want to compare them. There's a thing called a quantile plot. You literally, to pick a quantile, say the 0.5, I've seen half the data, or a 0.75, I read off the values of X, the values of data I would get for that quantile, and I plot one against the other. If the distribution is the same, you get a straight line, Y equals X, okay? But it might go off, it means the distribution's changed. So this is a really good way of testing for changes in distribution. And that's what we did here. And you find, I'll put it on its side by doing it X2 minus X1. So now it's a straight line instead of sticking up, okay? And you can then see different behavior either side. This is for AE at 0.75. It does one thing and then it does another. So this is, if you've got a multi-component distribution, the data tells you where the components are. Then you might want to go and fit them as we did for the tail end. So that's quite useful. So that's where I got the numbers from. I got the data to tell me. So the data is telling me where the different physics is happening, which is quite nice. Okay. Well, that was all about values, the values that you observe. But of course, we don't really want that. We want to know about events, right? Bursts. So I'm going to talk a little bit about bursts now and an interesting property of bursts. Okay. So what do I mean by a burst? Okay. You've got your data doing something like this. And I pick a threshold value, you know, everything above that, well, it's a storm, and below that, it probably isn't. Okay. So it's a very rough way of doing it. And I can count or find when there's an upcrossing. Okay. So how many times the thing go up and how long it lasts, and how I could integrate underneath and get the size of the burst if I wanted. Okay. So this is a way of identifying bursts. There's lots of things about how can you tell it's one burst or two. Ask me about that, but you have to think about that. Okay. If there's a little wiggle or what you do about that, which is kind of interesting. I mean, you vary the threshold. There's lots of things one could do. There's an interesting property of bursts, okay? And it's the following, that if I take my data, okay, and I ask for the mean duration, how long I spend above the threshold, and I ask for the frequency of upcrossings, which is 1 over the return period of the upcrossings, the return period of the events, okay? These two things are related by just the CDF itself. So just the CDF, because the CDF, if I pick a threshold, tells me how often I'm above the threshold. So how often I'm above the threshold in the time series, you know, is telling me that there's, you know, it's related to the duration, how long I'm above and how often I go above. So on average, how often I go above and how long I spend up there is just related to the CDF. Okay, so this is a small part of something called crossing theory. What this means is I've got a relationship like this. If the duration on average of the bursts is related to the average return period and the CDF where I pick the threshold. Okay, so it magically, without actually doing anything about the bursts themselves, I know something about them just from the data. So now think back, I said, oh, the thing doesn't change, or I know it drifts up and down in a simple way with the cycle. Maybe I can do something about events as well. Okay, so this is a really nice graphic Aisling has made, and it's time versus value for AE and minus SMR, okay, for 4 solar cycles. And we've stuck the solar cycle on, that's the red thing. So you could, it's this monthly sunspot number, right? So you can just see where the solar cycle is. And then we just plotted quantiles, okay, and shaded it in. And so you can see, as you'd expect, the thing goes up and down. So it's easiest to see in the SMR. You can see that solar max, it kind of goes up. You know, the quantiles go up and at minimum it goes down. So the value of SMR is going up and down, the kind of values you see. But of course, it behaves differently at different quantiles because, you know, distribution kind of floats up and down. And the question is, how does it do that? Does it just slide up and down? Does it change? What does it do? Okay. So thinking about this crossing theory again and what you've just seen, we've just shown that C goes up and down with the solar cycle, okay? So therefore, if I ask about an event and I say, you know, say I say I'm interested in an event that lasts a day, then events that last a day, I immediately know for what's happened, my value of C, what's happening to their return period on average, not in detail, on average, okay? Or I can say, well, what about events that happen once every 3 months, how long do they typically last? And it just depends on C. And now I know how C goes up and down with the solar cycle, so now I can say something about this. So we were thinking calling it, it's like an activity parameter. It's literally because what's controlling it is how often you spend above the threshold, which is how active you are. So this might be a useful way of thinking about the overall kind of space climate, that we're looking at as it goes up and down with the cycle. Okay, so just to kind of explore that a little bit. So all these plots are time in years along the bottom. You can see the 4 cycles. The black line on all of these is the sunspot number again. And what we've tried to do, I'm just showing this for SMR, we've done it for lots of things, is plot this guy on the top is burst duration, okay? And so you can see, okay, it does lots of things, okay? It kind of goes up with the cycle, but there's peaks when it's at minimum as well, okay? This is the return period, okay? And this is the same thing, just zoomed up, because of course the quiet cycle minimum, the 24 minimum, 23 minimum is so huge. And again, it sort of does what you expect, that it's longer return period at the minima and smaller at the maxima, but there's a lot of detail. But if you plot one over the other, okay, which is the activity parameter, you can now see, look, it just really nicely follows the cycle, okay? So there's a lot of detail in how R and tau independently sort this out. There's a lot of detail, which is interesting. But when you form the ratio, it just goes up and down the cycle because it's just controlled by the CDF, which goes up and down with the cycle. And as you've seen, that goes up and down in a kind of reproducible way that we know the distribution for it. Okay. Oh yeah. So of course, the thing to be clear, when I talked about thresholds, I talked about a straight line. I drew a straight line on my plot and said, oh, it's a value. And that's what we just looked at here. So these different colors were 100, 40, 60 nanotesla. Okay. You could say, okay, we know the thing is floating up down with the cycle. The quantiles were going up and down. So why not instead choose a threshold, which is the quantile? Now the threshold will go up and down with the solar cycle. Okay. And so tau over R is now constant because that's just given by the value of the CDF, the quantile itself. Okay, so that can't change. So I fix this guy now. Okay, and now what I'm left with is the stuff which is not just the floating up and down with the cycle. And you can see it here. Okay, these things, now you can see the changes that you get at maximum, the fluctuations, and at minimum are kind of roughly the same. So this is eliminating the kind of solar cycle pushing up and down, and what's left is other things. So this could be quite a good way of kind of decomposing the data. Okay, that's nice data. Okay, it's nice, not actual magnetometer measurements for 4 cycles, 5 cycles, but we'd like to go further back in time. And now things get a bit more grubby, okay, and that's what I'm going to talk about for the rest of the talk. What we have is a thing called AA, the AA index. And again, remember, we've got this problem. We need to deal with the background. So we can't just take 1 point. So what's been done, and this is Mayo's idea, that you take, 2 antipodal points. So you've got the UK and you've got Australia, and you use those to construct an index. And we've got those back, from 1868, 14 cycles. Sounds great, okay. But what the data actually is, it isn't actually a measurement. What it is this kind of pen chart, okay? I think this is the one for the Carrington event, actually, but we've got these pen charts. And so basically, somebody would go every 3 hours with a little logarithmic ruler, a piece of paper, and hold it up to the thing and say, okay, that's a 3 or that's a 6 or whatever. This is the K index. That's what you've actually got. And then you take that and you reverse engineer it back into something that is called nanotesla. And that's what the AA index is. And there's a lot of difficulty. So I refer you to other papers. Mike Lockwood's got papers on this to try and clean this up and deal with various issues of things changing, because it's over such a long time that the geomagnetic pole moved. There's all sorts of issues. So there's a lot of work being done. People have thought about this. But that's the nature of the observation. So this is really a lesson in, well, what do you do when the data isn't very good? And what we want to know is about things like this, the Carrington event, how bad is the Carrington event? And this predates AA. I mean, there's a reason for that. People got interested in Carrington and the Carrington event, so they started making magnetometer measurements, okay? And the thing we're going to talk about is this. There was this really nice result that Bruce Suratani I think the story is he went to a conference and got chatting to people, and they found this data, right? And so this is one observation of what it is. It's actually magnetized needles on threads being observed across the room through a telescope. And that's why you see the data is not uniform in time. When it all got going, they all started to take lots of points. You can see there's lots of points around here. Okay, it's that kind of data, but it's quite a big dip. And this is what's caused the fuss about the Carrington event, that the value of this thing is large. Okay. So this is the question, you know, how bad are historical space weather events? They can be quite bad. We know we've had recent ones that are recent enough that they cause power blackouts and so forth. So, you know, how is it just expensive and inconvenient, or is it actually catastrophic? Can we just be resilient towards it? So this is, we need to know how bad it might be, get some estimate. Just to give you a flavor of what this data is like, I plotted, this is called a rank order plot. It's really just the CDF flip round, okay? What you do is you literally rank order, like this is a rank order plot. So this is the height of celebrities, okay? Celebrities arranged in order of height. And so I'm arranging my measurements of AA, it's going the other way, in order of size, okay, in this plot. And I'm doing it for, again, the last 1, 2, 3, 4, 5 cycles, because I want to compare it with DST. And that's what this plot's showing. You know, is it doing the same job as DST, or what is it doing? Or at least tracking it somehow. And you can see there's DST, there's the last quiet cycle, okay? You can see the colors again. And there's AA, and you can see the steppiness in AA is due to this problem that really it's coming from a K index. It's just that this logarithmic number, and it's been kind of munged in. This looks a bit different if you plot this with Mike Lockwood's estimate. But basically the underlying problem is in there, okay? Okay, so you can't really treat it as a time series like you normally would do, I would argue, but nevertheless it's following what DST is doing, so there's useful information in there. Okay, so rather than pick the maximum, you know, you might be DST say, well, what's the maximum value in the storm, or what's the maximum in a month, or whatever, to get an idea. You can't, this thing is clipping, so you can't do that. So what we're going to do something else, we're going to ask for, well, take the largest sort of 5% or 2% or 0.1% of records and ask, well, what was that value? Okay, to try and get an estimate. Okay, and so what you can do is you say, well, we'll do that. This is the top 0.5% in a year, non-overlapping annual averages, and compare it with what DST is doing, the maximum value of DST. Okay, for when you've got DST, and you can see they kind of follow a line. It's not perfect, okay. But you know, the AA is telling you something about what DST is, so we're going to treat it as a proxy for DST going further back where there is no DST. And again, you can plot, well, how does it go in time? Well, they follow each other, but not perfectly. So not perfect, but it can give an idea. And then just doing this immediately gives you some idea of risk, because you can say, well, it's a very crude measure to say, well, if DST gets more negative than -500, that's a great storm, or -250, that's a severe storm. I mean, it's a bit dodgy, because really what you want to know is the rate of change, but I don't know quite how to do that just yet. Okay, so we'll just go with this for the moment. This is the kind of numbers people talk about. And then you can read across and say, well, where would that have been in AA, and count the number of times that happened in the AA record. So now we know over the last 150 years, 4% of those years contained a great storm, and 28% of those years contained a severe storm. So immediately you get some feel for the risk. And then what you can do is to say, okay, well, we'll turn the AA estimate as described into a DST one and plot it. And again, this is a rank order plot. So these are years. It's the value that you would see in that year, the maximum value of minus DST as estimated by the top few percent of the AA, okay? And so you get something which you can kind of draw a straight line through here, okay? And then you can talk about how likely these different values were, how often they occurred. Okay, you could do something a bit more interesting. You could say, okay, well, what about the one we haven't seen? And this would be the Carrington event if it's bigger than all the others. Because this is a known distribution, and so we know where the next, if I start with rank 2, I know where the next one would be, and I know the uncertainty would be modeled uncertainties. This is a known result, so I can stick it on my plot and then say, well, what value of DST would that have kind of been? And we come out with about like -850 plus or minus, okay. And then you can compare this with this value from Suratani's plot, and that this is -1750, it's way up here. And this is really interesting. What it's telling you is that this estimate is not part of this distribution, okay? It's not saying it's wrong, it could be right, but it's saying if it's this guy, it's not part of this distribution, which means the physics required to produce it is not the same. And that's really important, because if you're doing you've got some nice model of the magnetosphere and you're modeling the impact of storms, that's going to work great for all this lot, but it might not tell you about this guy. And indeed, there have been ideas as to how this might happen. Okay, I mean, I showed this thing. The idea is it's called a Dragon King. Okay, this is Sornet's Dragon King idea. So this is a plot of city sizes essentially in France. Okay, and so Lyon, Marseille, and all that lot are on this line, but Paris is off the map. It's over here. In other words, what defines the size of Paris, because it's a global city, is the same as what defines London, New York, or whatever. It's not related to the other cities. It's related to different economics. Okay, it's different process. So for this guy, it's the sort of thing, and this has been seen to happen, that maybe you get multiple correlated CME. So the first CME kind of sweeps out the solar system and makes it solar wind very fast. Then the second guy comes along and goes really fast and is very effective. So that it's a kind of correlated extreme thing going on there, and that might happen. So that's the lesson for that. It's not that this is wrong, it's that it needs different physics, and then you don't know how likely it is, which is an issue. So that's what we can get out of that. But the problem with it, of course, is it's got no solar cycle dependence in it. I just average, looks over 150 years. So in this last little bit of the talk, I'm going to talk about how to deal with the solar cycle dependence for storms rather, but also for other things as well. So this is my kind of clock thing, okay? So the idea is to use a Hilbert transform. We know the solar cycle, and I'm plotting on the top here. Okay, sunspot number. The length changes and the height changes. Okay, never quite the same thing. Okay, what do we do? And one way of dealing with this is a Hilbert transform. So the idea is if you think of things that are vaguely oscillating. So if the real axis S of t is my oscillating signal, I want to describe that with something which goes around in a circle. So it's got 2D coordinates, if you like. So this is called the analytic signal. So it's S plus IH, where H is the Hilbert transform. And so this is something which has A of t, variable amplitude and variable phase. But the phase clocks around roughly in time. So what you can do is use it to map a non-uniform oscillatory thing onto a uniform phase. The period is non-uniform, but the phase always goes round 0 to 2 pi, and that's what's done here. So we can do this with the sunspot number, and that's what's shown on the bottom here. And the coloured things are the maxima and the solar minima and the terminator. I'll explain what terminators are in a sec. Okay, so to do this, you have to make the thing go round 0, so you have to take off a running mean, and that's the blue guy shown here. Okay. Then okay, so great, now we've got a clock. Okay, so I can make something like this. So I've done this over the 11-year Schwabe cycle. And what I'm plotting, so going around here, this is phase, okay, 0 to 2 pi. Okay, and I can plot lots of things on top of each other now and line them all up. So first of all, these little dots here, so the red guys are the maxima and the green are the minima, so minima and maxima, okay. The blue guys are, there's this idea, Macintosh et al. Idea, that, you've got your nice butterfly diagram with the sunspots going down to the equator. When they actually get there, and this isn't just estimated from sunspots, it's EUV bright points and various things. When they actually get to the equator, that's the terminator, it's the termination of the cycle. So he's made estimates of that, and they're here. And when you stick these things on, we can now say, okay, let's put on things like the coloured things are the ghost flare catalogue. Okay, I've had to fiddle with the bins to make them fit, but basically the red are X class, the blue are M, and the green are C. And you can see these things, they basically switch on, okay, at the terminator, and then they're high all through maximum, and then they switch off somewhere. And so we call this the pre-terminator. Okay, the dots are AA values of the AA index. And so what we've done is said, well, we'll take the daily AA index and ask, well, what is its biggest value? Does it exceed 100, 200, 300, 400, 500, 600? So if you see a big streak, that means it's a very active day. And again, you see they switch on here, lots of active days, and then it goes all quiet. Okay. I drew this line here just by reflecting this, okay, into here, I said, well, just, I don't know why that's there, but, you know, you can see the minimum is now just bang in the middle. If I just take, you know, 4 pi over 5 there, that's another 4 pi over 5 there. And it roughly tells you where this thing is. That's not exact, but I just think it's quite neat that it kind of does that. But there's more detail I'll get to in a second. Okay, so this is the idea of how you can talk about these things. Now, we want to put numbers on it a little bit. So if I unpack this, and so our phases along the bottom here, okay, and so it's a normalized 11 years. And I'm binning the values of AA up here, and you can see there's basically, where in this quiet period, there's like a big hole, okay, except for the weaker events, okay, which is, you know, as you'd expect, there's a declining phase, more on that in a moment. But, you know, the large events, you now can say, well, actually, oh, they don't really happen. Only like 1.5 to 2.5% of them happen in this quiet phase. So they're very unlikely, okay. Interestingly, the flares, regardless of their size, roughly 6% turn up in the quiet phase, okay. So there's something else going on here, which we'll come to now. So this is so you can now talk about the solar cycle dependence of these big events, okay, to sort it out a little bit. And you can map back, once you've figured out where the switch on and the switch off are, you can map them back into time and go look back at the data. So you don't have to work in phase. Okay, so the final thing is this. So we've talked about amplitude, exceedances in AA. There's also time structure in AA, because you get, you know, the kind of garden sprinkler effect, you get high-speed streams, all right? So if you've got a big group of spots on the sun, they'll, you know, they'll go around a couple of times and you'll see something recur on the solar rotation period. And this is well known, okay? So this is a paper, this is Sargent, 1985. He looked at the correlation coefficient, you know, for successive 27-day pieces of the data and plotted it, and noticed that there was in fact a Hale cycle dependence, two Schwabe cycles, so a complete magnetic reversal, you know, from up to down to up again. And this is his plot, okay. And so what we did was kind of redo this, you know, because now, you know, I mean, you know, imagine what we're doing this in 1985 and doing it now. It's a hell of a lot easier, okay. So this is the idea. So we said, well, now we could just calculate the autocovariance. You know, we could just do a running autocovariance. This is what's being shown here. And this is a model. I built a little model. So I've got 27-day recurrences, the first part of the model, and then I've just got a bit of noise in the middle, and then I've got recurrences which are just randomized, so no 27-day, and then I can push this through and say, okay, well, if I can look at the 27-day autocovariance here, and you can see it does something. I can look at one at some other number, say 10, and that's the red guy, so that's what the noise looks like, okay, and so forth. But you can see this is awfully spiky. So what do I do? Well, what Sargent had to do was kind of smooth it. And he did a complicated thing, okay? So I could smooth this spiky thing, and then I can see that the sort of, you know, a very sort of low time scale Hale cycle dependence. But I can do something better than that. I can actually use the Hilbert transform to sort all the cycles out, and then kind of bin across the cycles instead to get higher time resolution. But just to show you this thing working, this is doing it actually on the AA index itself, and you can see the red guy is kind of, you know, it kind of goes big, small, big, small. It's quite rough, but you can see there's a Hale cycle dependence, which is what £100. Okay, so now I'm going to build a Hale cycle clock. So now it's a 22-year clock. Okay, and on here I'm plotting the grey stuff is the F10.7, okay, which is, you know, you can see it's quiet when it's quiet and so forth. And the red line is my estimate of recurrence, which I'll talk about in a moment. But before I do that, just to have a look at the thing itself, you can see here are the maxima, and you can see that, you know, the average drawn through. So they pretty much clock. The minima, there's a bit of a difference, and the terminator, there's a bit of a difference. So there's a Hale cycle difference in when these things turn up, although it's quite small. We haven't got many to count, okay, so that's why I haven't made too big deal about it. Okay, this guy, the red guy, what I've done is get the 27-day autoconvariance, and I put everything on the clock, so everything is, you know, on the normalized 22-year cycle, and then I've binned across in time, so I hadn't had to smooth it. And so now you can see, you can resolve quite sharp changes. And so the point is the changes are sharp, that here at maxima, it's a mess, okay? The solar wind is very disordered, but as we come in, to minimum, it becomes very ordered. And it's now you can clearly see the Hale cycle difference, that this guy pops up at the pre-terminator, the thing we talked about before, and then kind of crashes at minimum. On odd cycles, even cycles, it stays high a lot longer. Okay, so it's known that it does this, but it's kind of really nice to resolve it. And you can see it more clearly here. Okay, so now I'm lining up the amplitude and the phase information. So this is the binned, detrended, 27-day autocovariance, and you can see here it pops up and goes down, pops up and goes down. These are the minimum. Okay, so in both cases it drops at minimum. So this you can see these are different lengths. So you notice a different length. So what's really happening is we've got an extended kind of declining phase in even cycles compared to odd. And you can see this in the AA exceedances, so the big storms don't really happen in the quiet period, but the kind of more moderate ones do. And you can see here they are in the declining phase. Okay, so this thing, I mean, basically the rate of change here is on the resolution of the method. Because we're doing a running autocovariance, you have a window length. Okay, you can't have it too small, so it's really on the a few window lengths. It's as good as we could tell. It could be sharper, but we can't tell. Okay, and you can stick other things on the plot as well. So like you can stick on the galactic cosmic rays, which they're known to have a Hale cycle dependence. Okay, you can see it here. Okay, but we can now compare it with what's going on with the AA occurrence, which is the solar wind structure. So you can directly line them up. So you can see here, following an odd maximum, you can see they both go up together. And then the solar wind becomes disordered, but the galactic cosmic rays stay high. So there's at least two mechanisms going on here. People have talked about this for a long time. As you reverse the polarity, of course, you're talking about protons coming in, they come in a different route, okay, and that could account for it. But of course, it's also relates to the disorderedness of the solar wind as well. So there are these two things competing, and you can see them both in the plot, basically. Okay, and there are other things you can do as well. So this is looking at sunspot latitudes, and again, you can see a little Hale cycle effect in here that it doesn't look quite the same, and so forth. So I just want to wrap up now so that people can ask me questions. So I've covered a lot. As I say, it's a very kind of surface level discussion, so people can ask me questions about how the detail. There's a lot of detail of checking this stuff and thinking about uncertainties and so forth. But I've tried to kind of break this up into two kinds of problem. One is you've got lots of observations. They're not where you want them necessarily. They're where you can put the magnetometer or whatever. And they're giving you minute data, and they're giving you it for several cycles. And you want to compare lots of events, and you can't just look at all the detail. I'm very struck. The last time, when that was a while ago, I walked around the posters at AGU, and there were many posters with lots of plots of pictures of the Earth and the aurora or whatever it was, the magnetometers, whatever it was, plot, time series, trying to look at a time series of how an event's evolving, and then how another event's evolving. And you just cannot do statistical studies based on that. You need to put a number on that, and then compare that number between your 100 events. And then you can start saying, well, do all substorms do this, or do some do something different? Maybe they do something different with the state of the solar wind, blah, 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 whatever. You can really start nailing that down. And so that's the power of this network idea, okay? Is to kind of reduce the complex data down into a number that's useful. And then the other thing, just looking at one point, okay? And we talked about lots of things. We talked about just this really rather interesting property, it would seem, of plasma parameters. I mean, this I talked about SMRAE. It's true of solar wind plasma parameters as well, that you've got this, if you look at the piece of the CDF containing the events, it kind of slides up and down with the solar cycle. Basically, the distribution itself doesn't change. And then that also means that the bursts, the average properties of the bursts, have that behavior as well, because they are constrained by what the CDF is doing. So that's really interesting in terms of thinking of, I wouldn't say predictability, but reproducibility, that if you know what the next cycle is going to do in the rough, then you can say in detail what these things are going to do. And then this idea with the Hilbert transform, how you can, compare things on a uniform time base when you've got a roughly but not quite oscillatory thing going on. I'll stop there. So hopefully people can ask me questions. Hello?
Hello,
Manuel's got his hand up. Yes.
Yeah, thank you so much for your excellent talk. I think it was really, really great. And is there any question for Sandra?
We've got a hand up from Manuel Grande.
Sure.
Ask you to unmute yourself. You can ask your question.
Sandra, wonderful talk, of course.
Thank you.
So 2 comments and a question.
Right.
First of all, I mean, your Schwabe cycle plot, I think, showed perfectly the Jane Feynman thing of
yes.
4 years on and 7 years off, other way around.
Yeah. Let me just go back. Yeah. This one. Yes.
So that just shows it perfectly, doesn't it?
Yes.
It's great. The second one, which also I thought showed something perfectly, was when you were talking about your threshold, your Tor upon R parameter.
Yeah.
And in recent solar cycles, as we know, the solar cycle has bifurcated. One the other way, one that one. Yeah. If you look in the left-hand corner there, you really see the progressive bifurcation beautifully.
Yeah.
And I like that. But my question was, I remember a talk a few years ago now by Paul O'Brien.
Right.
And he had actually looked at the statistics of various parameters, and his methodology was he'd actually used some algorithm, whose name escapes me at the moment, but it's used for predicting stock market outcomes.
Right.
But what he showed was that DST is bounded, which was, I think, apart from the Carrington event, what you were also showing.
Yeah.
That it. But what he also showed was that solar wind velocity was unbounded, and I wondered if you'd tried using solar wind velocity. I know it's not such a good data set, but whether you tried using that.
No, it's a short answer. I mean, we did look at a bunch of things, but no. But I don't know. Gosh, I'm not quite sure which bit. Which when you say tried it, do you mean this, or do you actually mean this? This kind of stuff.
Yes, I mean that.
Yeah. No, we did. We've tried a number of parameters, things like magnetic field and things. Okay, when we talk about this bounded, we should be a bit careful, because what's going on, I mean, if we look at, like, this is DST, okay, because this is what we're talking about. You can see it collapses quite well, but then it kind of rolls off. Okay, and then it's all over the place. So I don't know. Well, it's bounded in the sense that you're running out of data there. All right. So, you know, other quantities might not do that.
I mean, I think he was finding with, as I said, this algorithm's name I can't remember, was that basically you don't expect to see a DST bigger than the biggest one you've seen, whereas there's no earthly reason why you shouldn't see a solar wind velocity much bigger than you've seen before.
I mean, okay. I mean, I don't know. I'm guessing he did something like this. He was looking at this distribution fitting. I'm guessing. I don't know, but yeah.
I can't remember now. As I said, it was one for predicting, again, you know, unusual stock market events.
Yeah. Okay. Well, yeah. I'm guessing it's something based in distribution. That's what I'm guessing. In which case, yes, you can see these things all roll off, basically. Yeah.
I just wondered if you had any plans for that.
I could do it. My worry is I'd have a look at what he did, because the problem is you always run out of data. It's a finite sample. You're trying to distinguish. Okay, the running out of data is it because I've just got a finite sample, or is it a genuine roll off? And I mean, that's tricky. Why is that tricky? So you see the light. I didn't talk about it. You see this kind of coloured stuff. Those are the uncertainties on the estimate of uncertainties on the CDF really, and they're huge because you're running out of data. So you're in a region where you're running out of data, and so the uncertainties are blowing up. And then to answer the question, well, am I running out of data just because I'm running out of data, or is it because it's rolling off? It's actually quite tough, and I'm not sure how to do it. Okay, that's my reservation. But I'd have to look and see what he did. You know, maybe he was doing something else, but it would have been something based in distribution. You know, the thing about the Carrington event is a different statement. I mean, people argue about that. I should just clarify that, and then I'll talk something else. Oh, that's another question. If I go back to this chap, this is very contentious. this is not a measurement of DST. It's an estimate based on this guy. Okay. And people have very strong views both ways, as I discovered when I tried to publish it. You know, I had one referee saying, well, of course that value's right. And then the other referee saying, no, we know that value's rubbish. Okay. Because it's one measurement, it's not DST. So, I mean, I'm open to this. You know, I'm not saying it's one or the other. I'm just saying it can't possibly be the same physics as the other ones. All right. So it's a slightly different statement. But just to clarify that, but yeah, in case I don't want to get in a big argument. Okay.
Great talk.
Okay, thanks.
Yeah, I think we have another raised hand, right?
Yeah, Luke, if you would like to unmute yourself.
Hi, Sandra. Can you hear
Hello?
me?
Yeah, yeah.
Great. Thank you. That was a really excellent talk. I really enjoyed it. Earlier this year, we actually discussed Hale cycle asymmetries.
Yeah, we did.
Phase differences between the maximum, minima, and terminated and odd and even cycles. And I was left with the impression that we concluded there weren't enough samples to have confidence that the differences were real.
I'm going to stick the plot up and people can come to their own conclusions as to what you do with this information. So basically, yes, there aren't very many. And this is a real problem when you're trying to do, you know, you've only got like 14 or whatever solar cycles. So if you now do Hale, you've only got, you know, 7 or 8. I mean, you don't have that many cycles end of the day. And this is the problem with trying to do this stuff. And you can see what we've got. This is the data. And you can draw lines through where the averages are. And then you can see, you know, whether you know, the trouble is you've got you can throw statistical things at these to try and quantify, you know, how likely they are, you know, to be, you know, the question we're asking, by the way, look at the blue guys, you know, are they exactly opposite each other or not? That's the question we're trying to ask, but there's not very many of them. Okay. And you might say a suggestion that they look like, no, that one's slightly, you know, to the south, but, and you can put statistical measures on this, but my opinion is that you've got so, even the statistical measures, because you've got so few, the uncertainty on the uncertainty is large. And you end up not concluding anything more than just looking at it and thinking, oh, well, it looks a bit different, but that's all I can say. You know, I don't, you know, there are just very few. So yeah, I think that's where we are, okay? I don't think I could do much more than that with it. And it's a problem. It's going to be a problem. I mean, all these things, you know, some of the other quantities that I've been sticking on these plots, like the GOES flare catalogue, it's only 4 cycles. You know, you can do it, but we have to bear in mind most of these things are not available for that many cycles. And clearly the sun shows changes on much longer timescales than this. So, you know, all this stuff you have to take with a massive pinch of salt, I think, because we haven't got that many solar cycles. Hello?
Yeah, okay. Yeah, so I was only really wondering if anything had changed since then. So
well, I haven't got any more data, no.
No, okay.
No, so it's no. I'm going no. I mean, no. We're stuck with this one. I mean, and I think it is the real problem. You know, and doing nice statistical things can only get you so far. You know.
Cool. Thank you very much. It was an excellent talk.
Cool. So, do we have any other questions?
I have a question. If Sandra's got time to stick around, because I know you've got another interview to go to.
I've got a bit of time. It's all right.
Okay, I was going to ask about your method with the correlations with the networks.
Oh yeah.
And so it's my understanding that you use linear correlations. And cross correlations there.
Yeah.
But in order to do linear regression, you have to make the assumption statistically that you have a set of independent variables, right? But this is a current system that we're looking at. Can we really assume that each time step and each point in your grid essentially is independent? And how do you go about that? Do you do anything to the data beforehand to take that into account? Or
no, I don't. And I'm going to I just want to unpick this a little bit, because imagine, I mean, the problem we're trying to solve. Okay, imagine it's like you're sitting in a bay, nice sunny, and you look at, a boat passes and it produces a wake. Yeah. Okay, and a wake is traveling across the bay, and you're looking at 2 buoys, and the first one goes like that, and the second one goes like that. Okay, this is the problem I think we're addressing, and I think. Are they independent? Well, in what sense? I mean, that the wave, if they're in the sea, there's the one wave. The buoys are independent of each other. They're not connected to each other except by the wave. Okay, so therefore, in my view, doing cross correlation between those two to calculate the propagation speed of the wave is perfectly appropriate, and that is what we're doing. Okay, so we're assuming that we're not, you know, we assume that the only connection between these magnetometers is the overhead magnetic field that they're seeing. They're not connected in any other way. Okay, that's gone. Now that you have to think about, because remember, we're subtracting off a background which does in fact correlate them, and that's something that I kind of mentioned very briefly, but that sort of thing is what you have to take care of when we look at the thresholding, and we just spent a lot of time on that because that varies. So even if nothing else was happening, these guys would effectively be correlated by the fact that there is a time varying threshold on them. Okay, on the observations. But I don't quite understand beyond that. If you think about, forget, if you put that to one side, the correlation thing. You know, if you've got your two buoys, then they are not connected to each other except through the wave. What you're doing is literally, you're assuming that, you know, because it's Fourier, you're assuming that it's a Fourier decomposition, okay, and that you can represent the time series as a bunch of waves. I'm looking at how this wave, you know, propagates to here through correlation, and that's the assumption that I'm making. So in that case, you know, you don't do anything else to them. Okay, so that is what you're doing. So the assumptions, there's this whole story with the threshold and the background. Okay, but it's also that the big assumption is the Fourier assumption, that you're taking a time window which is finite and doing essentially a Fourier decomposition and comparing it with another one. And there's a whole bunch of things about that. One has to think about stationarity within the window, which isn't really okay. You've basically chosen a bandwidth of which you think, I'm going to treat it as quasi-stationary over that period, the length of the window. Okay.
Yeah, that's what I was wondering.
That's what you have to worry about.
There's two independent things there. There's the space and then there's the time aspect. So that's what I was wondering about. In
time, so you know, in space, you assume the things to worry about in space. There is the business of the calibration, if you like, the removing of the background, which is a source of correlation. And in time, is the Fourier assumption, which is the stationarity, that you've got a certain length of window. And practically you're saying, well, I want the window to be big enough that the cross correlation is meaningful. I've got multiple cycles in there. Okay. And I can't resolve past changes quicker than that window. Well, there's more to that actually, but you know, if you take the window too long, you start to cease to resolve the changes. Right. But yeah, it's a tricky one, and it's yeah. Did you look at the autocorrelation?
Sorry, did you look at the autocorrelation at all? Was that?
Yeah. I mean, I mean, we plot these things. Yeah, absolutely. Yeah. So, and you know, because you wanted to check, there's all sorts of things you need to check. I mean, well, you have to check that. As I say, there's this business of the threshold. The threshold, now here's the thing, you know, the different stations have different sensitivities, and they depend on what the station is, where it's located, but also, you know, when the Earth turns around, that changes, okay? When the season changes, that changes. So you have to, basically, you take a month around the event and you calculate the cross correlation between all the pairs over that month. That would just happen anyway, okay? And then you say, okay, I'm going to build my network such that each station, on average, always gets the same number of connections, so it has the same chance to be connected as every other. And that means each station pair has its own threshold, which changes in time. Each event, you calculate it. It's really, you know, otherwise, all this stuff just folds in, and you don't see the effect of the event. You see the effect of all the other background stuff, which is doing spatial correlation. So yeah, there's quite a lot of work in thinking how to do this, and for different problems you might do this differently. I think Nick's got his hands up. He wants to say something.
Nick wants to say something.
Maybe this could be the last question, because I think we are running a bit late and many people are actually leaving. So
yeah, I mean, it's a very, very brief suggestion. In the previous question, I think there was mention of cross correlation, but also mention of linear regression. I think when you're regressing X against Y, it's like doing a cross correlation at zero lag. Okay, and therefore, in some sense, I think you're not worried. You're assuming there are no correlations at any of the other lags to worry about.
Yeah.
Whereas I think that's the conceptual difference. If there actually are correlations at all the other lags, there are subtleties in your linear regression that you're not really allowed to ignore. So a cross-correlation function is at all the lags, whereas just what the linear regression that we did at school, in some sense, is just lag 0. Yeah, and I think that may be of some relevance to your original question. I mean, I can't swear to that, but you've made me think about that, and I think that's the difference. But I mean, I'm not claiming that I'm right, but I'm suggesting that's the difference between the linear regression problem and the cross correlation problem. Okay. All right.
Cool. So thank you very much for coming, Nick. And I think we need to conclude here because we are now quite late. Yeah, it's now almost 10 minutes past noon. But yeah, I would like to thank you so much, Sandra, for the absolutely amazing seminar. And yes, a quick reminder that in 3 weeks we will have our autumn Miss meeting, and we really hope to see most of you in there. And also our next seminar will be on the 7th of December, and it will be by Adam Masters. So yeah, thank you so much for everyone to be here today, and really have a nice day and a nice week. See you.
Thank you. Right.
Actually, Sandra, you have a lot of comments in the chat.
Oh, hang on. Let me just see.
Sure. I will stop
I have
the
to figure out how
recording.
to stop sharing. Okay, if I stop sharing,